Welcome, everyone, to a virtual event hosted by the University of Utah's Department of Materials Science and Engineering. My name is Michael Simpson, and I'm currently serving as the chair of the department. I'm joined tonight by the Associate Chair, Taylor Sparks. I think we have a really interesting program. I'm glad you all have joined us. I'm going to show the agenda. So tonight's agenda, start with a welcome by me. We're going to show a video made by a team of our own students, undergraduate students in the department. Then we will jump into introducing our panelists, who are all inventors who are affiliated with our department one way or another. Several are faculty members and at least a couple are alumni. Then Taylor and I will ask some questions, and then we will turn it over to the audience to ask more questions. So you should see a little box at the bottom of your window for questions. So please type questions as you come up with them, and then when we get to that time, we'll try to answer as many as we can. All right. So I want to set the stage by showing you that all the different kinds of materials that our students study and research: metals, ceramics, polymers, composites, biomaterials, you name it. This is one of our panelists, Jeff Bates, who invented a new ski wax, who'll be talking to us later. We actually offer 2 different undergraduate degrees, but we have options for master's degree, options for an emphasis. It's really a great deal of versatility and flexibility that we offer to our students. Finally, I wanted to let you all know that our department is, in its current state, is very new. Just last year, we combined metallurgical engineering and material science engineering to make what I think is an amazingly diverse and inclusive materials engineering department. So next, I'm going to change over the video, and I'm going to have Taylor introduce it. Taylor, you want to say some words about the student team that made this?
Yeah. So as Mike said, our department did just undergo a merge last year, and we are excited for the changes this brings. And so one of the things that we thought we'd do is update a portal into the department and show you some of the things that we have going on. So there are student groups, there's centers, there's activities. And we wanted to highlight some of those in this video that was made by some of the undergraduates in our department, both students in lab classes, as well as some of the student body groups, MASS, for example, the Student Advantage chapter, and some others. So without further ado, I think we can go ahead and hit play.
Okay, so if y'all don't hear the sound, please let me know and we'll address that.
As the only materials science and engineering program in the state of Utah and the smallest department within the U's College of Engineering, students are able to thrive in environments that nurture their development as engineers while also providing the opportunity to become a part of a close-knit community that includes inspiring professors and alumni working at the forefront of scientific findings.
Hello, my name is Brenda Wicks. I'm an academic advisor for the Materials Science and Engineering Department. There are 2 degrees that are offered in our program. There's the Metallurgical Engineering Bachelor's of Science degree, and then there's a Material Science bachelor's degree from the College of Engineering. I've been an academic advisor with the Metallurgy Department for 3 years, and I've been the academic advisor for Material Science for 1 year. Yep. And then the 2 of those programs merged together. There's a lot of similarities between them, so to have some of that just stop in the office and ask a professor a question and so forth. However, I think even during COVID, they have made themselves as available as possible through Zoom and group chats, and are accessible through email. The thing that makes our department and our programs unique is that you are educated in the basics of math, chemistry, and physics. And this is in order to prepare you to take a variety of materials science and metallurgical engineering courses. You can consider these courses tools in your belt of education, understanding, and application.
An important aspect of material science is trying to predict when our materials will fail, and then to analyze what factors contributed to that failure. Oftentimes, these factors are the result of material processing conditions. There are many tests that we can perform to do failure analysis. In this lab, students use a Charpy impact tester to break samples of cheese and then dry them in a toaster to correlate how the moisture removal in the cheese-making process will impact the failure conditions of the cheese. This is valuable information because sometimes, as with cheese, we want it to fail at a certain point, such as when biting down. This lab also demonstrates that there is much more to material science than just polymers, metals, and ceramics, and that we can gain insight into almost any physical object by using a material science perspective.
Hello, welcome to the Materials Characterization Lab. Come on in. The Materials Characterization Lab is a lab full of equipment that we use to characterize materials, obviously. We use the lab for both researchers and industry, so on-campus and off-campus projects. And when people have made a material or a device, they can bring it to us and we help them figure out whether it's working properly or if they need to tweak their design a little bit to get things to work. So some of the machines that we have, obviously we've got some pretty basic like an analytical balance here, but then we get a little more complicated. This right here is a thermal analysis, it's called a DSC. This tells us where there are phase changes, such as from solid to gas or gas to liquid, or any of the combination of phase changes. So DSC, this one goes down all the way to negative 150 degrees Celsius. So extremely cold. We often use it to freeze plastics and see kind of where their freezing point is. This right here is an Absorption Analyzer. It helps us know the surface area, the pore size, and the pore volume of very, very small materials. Think about like a foam, a really light fluffy foam. This could tell us exactly how big the holes are in that foam, down to a couple of angstroms. This machine here to my right, as well as the machine on the other side here, these are both called Xrds. Xrd tells us what phases are present in a material. So it's typically used in like mining or geology. They're going to tell us whether there's silicon dioxide or aluminum dioxide or any number of other things in your powdered sample. Then this here in the corner, this is a particle size analyzer. It does exactly what you think it does. It tells us the size of particles all the way down to a couple of nanometers. So as we're going through the lab, some of them are in various states of being used or functioning, and the lab is changing pretty regularly. We get new machines all the time. But those are some of our more commonly used and helpful machines. I have lots of stories from working in the lab. Since we work with so many people, we really get a wide variety of things. We have an internship in the MCL where students of material science and engineering can work for 2 semesters in here. They get class credit for it. They learn a lot of hands-on skills with the machines. And they also get a chance to kind of work with the researchers and the industry people that come into the lab. So about a year ago, or within the last year or so, I had my interns. There were 7 of us. It was midterms, everyone was super stressed, and I had sort of gathered all my interns together. And I had found a dragonfly and just dead in my garden, which I was sad about. But I didn't kill it, it just was that way. And then I brought it into the lab and we just did all of the characterization we could on the dragonfly. I had the interns come up with ideas such as how much UV light makes it through a dragonfly wing. What does a dragonfly look like under an electron microscope, which we actually found quite a few little hairs and fun things. What is the surface area of a dragonfly wing, that kind of thing. So we were able to ask a whole bunch of fun questions about this dragonfly, and then they were able to apply their skills on the machines that they had gained through the internship to analyze our dragonfly.
I'm Tristan Lindgreen. I'm a student technician at the Roger and Don Crew Center for Metallurgy Student Research. We're a facility that specializes in providing resources for student researchers to conduct their research and analyze their samples and do all the things they need to do to be successful in their research projects. We have all sorts of equipment. We have like a BET, a DSC, an SCM, sputter coaters, XRD. And I'm in charge of training students to work with those pieces of equipment. We get new ones in all the time, so I've always had to be learning how to use these things and train others. I also run customer samples, so people who need their samples analyzed but don't have time to come in and do it themselves, they can submit it to us, and technicians like myself will analyze that for them and get them the results they need.
University of Utah engineering students also have full access to Lassonde Institute, which offers an assortment of entrepreneurial development programs and equipment, including 3D printers, laser cutting, prototyping rooms, and more to help students pursue their entrepreneurship goals. The Nanofab Lab is yet another resource available to students. Located in the Sorensen Molecular Biotechnology Building, the Nanofab features a range of surface analysis equipment, including multiple different microscopes and a clean room specifically developed for engineering at the nanoscale.
And this is a high-resolution scanning electron microscope, and it's coupled with a focused ion beam. So what this allows us to do is image things at very high resolution. So we can actually image down to about 10 nanometers, just little snippets of some of the research we've done with faculty, both here at the University of Utah and other schools as well. And so it touches on a lot of different topics. And again, this really speaks to the very multidisciplinary nature of a lab like this. So you can see research coming from metallurgy, coming from bioengineering, coming from electrical engineering, coming from bioengineering again, coming from materials science, chemistry, materials science, chemical engineering. The list goes on and on. And again, these are the tools that we provide researchers to peer down to scales that are on the atomic level, as you can see here. So a very important helping role we play with lots of different research groups across campus and beyond. Wet processing, so this is chemical etching. And then the orange room you see over there is where photolithography is done.
Students are able to be at the forefront of scientific findings while also having numerous opportunities to connect with other students by joining the various student groups on campus. Among these groups are the Materials Science and Engineering Advancement Society and Materials Advantage, which promote communication among students and their instructors, as well as provide a voice for the undergraduate Materials Science and Engineering student body.
I talk with students on a regular basis and find that they are excited about all of the opportunities that there are in material science. And it's always exciting for me to see that typically a student's sense of curiosity only grows in the program. It doesn't shrink. I talk with a lot of students that are just wowed by all that there is to learn and explore.
All right. That's awesome. Thanks to everyone who put that video together. So next, this is the main part of the evening. We're gonna introduce our panelists, and so I'm first gonna go around and introduce each of them, and we're gonna ask them to each talk about themselves for 5 minutes or so, 5 or 10 minutes. So first, I'd like to introduce Dr. Gavin Garside. He's currently the lead materials engineer working for Spacex. Dr. Garside earned both his bachelor's and his PhD in metallurgical engineering from the U. Dr. Garside, please tell us more about yourself and your interests.
Absolutely. Well, thanks for having me tonight. It's a pleasure to speak to everybody. So after getting my doctorate degree at the University of Utah, I went out to a metals mill in Albany, Oregon, which is ATI Specialty Alloys and Components, formerly known as Huacheng, where they make a whole host of different specialty materials that include zirconium alloys for nuclear applications, niobium alloys for semiconductor applications, as well as linear accelerators, particle physics, all those types of applications, as well as high temperature metals such as C103 for rocket propulsion systems, as well as a host of titanium alloys as well. So that really gave a great experience for me to learn how metal's made. going from, ore or a intermediate product to final sheet, to final bar, different things like that that go out to OEMs for manufacture into actual components that are used for these specialty applications. After that, I worked at a company called Nanotechnology, which was a intermediate a job shop almost, where you could do different types of machining operations. There were 3D printing operations, different things of that nature. Before I was recruited by SpaceX, primarily because of my experience with ATI for their high temperature metals applications for rocket components, primarily C103. So after being recruited by SpaceX, I spent a lot of time working on the different engine systems that they have, primarily with the M1D engine, which is on the Falcon 9 rocket. There's 9 of them on the first stage, as well as the Merlin vacuum engine, which is on the second stage, and there's only the one of those. My primary focus, being very high temperature metals applications, is with the Merlin vacuum engine and the big bell that you see that glows on any of the launches. So there's that big giant red glowing bell, and that's all made from C103. So that's a sheet product that's welded together into this big giant part that's about the size of a car. And we've been working over the years to replace that with a much better powder route processing method, which decreases cost by half, as well as increases performance of the engine substantially, essentially by this materials development that we've done.
Thanks, Kevin.
Absolutely.
Next, I'd like to introduce Dr. Willa Cutler. He's currently a vice president at Corning. Dr. Cutler earned his bachelor's in material science and engineering from the U and a PhD in material science and engineering from the University of California at Santa Barbara. Dr. Cutler, please tell us more about yourself and your interests.
Sure, thanks for having me tonight. So I currently work for a company called Corning. Corning Incorporated is an old company, about 165 years old, and it's one of the world's leading innovators in material science, primarily in glass science, ceramic science, and optical physics. And we're a little bit of an old-fashioned company in that we still believe in inventing, making, and selling physical stuff. And typically we combine a materials invention and a process invention to create a keystone component that goes in a product. So those of you who have watched TV or use a computer or a tablet or a phone or the internet or drive a car have interacted with some of the components we've made. So I actually got hired into research and worked there for about 8 years doing materials research, primarily in inorganic materials. And after that period, I moved with a product that we had developed that a customer was interested in to product development. So in our vernacular, as customers become interested in things, they move from research to development, and then from development into manufacturing. And after about 5 years in product development, I moved with another product that I had helped develop into the marketplace, and lived in Germany for 4 years, essentially in a commercial role, selling the product from the new material that I had developed in the automotive market. And that was a very different experience, a lot of fun, taking something from initial product into the marketplace. And after that experience, I came back to the mothership, so to speak, and got put in charge of new technologies for, it was kind of like the home for the homeless, things that, technologies that had no division to go to, and worked on things like a miniature projector that goes inside your phone, and very different technologies, removing mercury from coal-fired power plant exhaust, and working on a microreactor for fine chemicals and pharmaceuticals. And then the last decade, I've spent in charge of technology for a $1.5 billion division of Corning that does pollution control for cars and trucks. So I work with all of the car and truck manufacturers around the world, helping introduce new materials and products that can remove gaseous and particulate emissions from their exhaust. So I found that it's a lot of fun to turn material science into practical solutions, and you know, you can make the world a better place and get paid for it. So it's a win-win situation. So thanks for participating tonight.
Thanks, Willard. Next, I'd like to introduce Dr. Jeff Bates. He's actually currently an assistant professor in our department. Dr. Bates earned his bachelor's and PhD degrees in materials science engineering from the U. Dr. Bates, please tell us about yourself and your interests.
Right. Yeah, thank you for having me tonight. So I just have some notes. I kind of prepared for this, but one of the things, like when I think about innovation, I think that really good solutions come from really good problems. And so I like looking at problems and understanding I like to understand all the facets of them before I start jumping into the solution. I also love developing new materials and thinking creatively about solving problems. So three that I'll talk about, well, I have a few that I'll talk about just briefly right now, but one of them is Shiro. It's a startup company that I have. So a few years ago, a company in Guatemala called Shiva, they asked if we would be willing to, so I specialize in polymers, and so they asked if we could develop a super absorbent biodegradable polymer that could be used in feminine hygiene products. And so we kind of jumped into this, and I had some students working on the project with me, but I didn't really love where it was going because the stuff that was going to biodegrade, even though it was biomaterial based, it was degrading into stuff that wasn't that helpful for the environment. So I kind of put a pin in it, and we just kind of put on the back burner for a little bit. And I love aha moments. And so about 4 months later, I had this aha moment when I was looking at some dehydrated rice and imagining the porosity and the absorbency of rice. And we don't use rice in the product, but it just kind of created a springboard for where we could go. Another one that I like, the very first one, I have a startup company with Professor Sparks called Utah Materials Research. And the very first project that we got with that one was called Clinch Brace. So there was an orthopedic surgeon and a sports medicine guy. And they really wanted to have a better way of wrapping arms and I guess wrists and ankles and stuff for gymnasts and athletes. And so they wanted to come up with a hot melt, like a heat shrink type of material that you'd put a sleeve on your arm or something on your leg. And then they said, okay, then you just use a hair dryer and then it sucks to your leg and it compresses the way that it needs to. But the problem with heat shrink materials is that the way that they're made is they stretch them out. So they heat them up a little bit, they stretch them out, and then they hold them until they cool down. And so then then they release them. Once you apply heat, then they go back to their original shape. So what would happen is when you put it around the joint, like around your finger, for example, and then you'd bend your finger, you just had a stretched out polymer wrapped around your finger. So there was no elasticity and there was nothing that's going to give it any support. So we came up with a really cool solution. I was thinking about, this is another thing where we're just kind of thinking about something else, but there's this concept called interpenetrating networks in polymers. It's like the Olympic rings. So they're all kind of connected to each other. And so we decided to kind of use more of a macro scale version of that, making these interpenetrating networks. But one of the funniest ones I worked on, the Poopery guys came to me and asked me if we could develop a polymer material that degraded when you flush the toilet so that it would release the Poopery material when you flush the toilet. So that was just one of the, I guess, more interesting ones that I got to work on. So some of the things that interest me, I really like complicated problems that appear to have no solutions, like the clinch brace one that I just talked about. But I also like to work with materials that are used in biomedical applications. And as a polymer engineer, I feel like it's kind of my responsibility to make sure we're not destroying the environment too much. And so we hear about microplastics and plastic accumulation in the environment all the time. So one of the things I look at with all of the materials that I work on is the whole life cycle analysis. So where do these things come from? when we are done with them, where do they go when we're done with them? Is it a cradle to grave, a cradle to cradle type of scenario? And so I want to make sure that we're not adding to the accumulation of plastic in the environment. But I also like materials and technology that people are actually going to use. I like it when I can go somewhere and point at something and say, I invented that. So I was at a doctor's appointment right after. So I developed this ski wax alternative material for DPS skis. And the very next day after their Kickstarter campaign launched, I was at the doctor's office and the guy said, do you ever work with chemicals? And I said, because anyway, it was part of the exam. And I was like, yes, I work with chemicals all the time. And he's like, well, what's your job? And I was like, well, I'm a professor in materials science and engineering. He's like, oh, really? What have you invented? And I was like, oh, I invented this really cool ski wax alternative material for DPS skis. And it was really funny. He's like, I just backed that last night. So we spent the rest of the visit talking about DPS and how that worked. But anyway, so those are some things that interest me. So some things that I'm working on, since I have 2 startups, I'll talk about those briefly, and then some of my research at the University of Utah. But with Shiro, for example, we're working on the world's first hot melt and pressure sensitive adhesives that are made out of biopolymers, and they're biodegradable. So we've been working with the world's largest adhesives manufacturer. They're called Henkel, and they are all over the place, all over the world. And so we're working on some of these adhesives for them. For Utah Materials Research, we were just starting a project where we're doing a series of experiments for the Purple Mattress Company. So they made something that everybody loves, but they don't understand what they made or how to make it better. And then at the University of Utah, we're working on soft robotic glucose sensors and actuators, contact lenses for drug delivery devices, and superabsorbent polymers. So those are some of the things that we've been working on.
Thanks, Jeff. Next, I'd like to introduce Dr. Jerry Stringfellow. Jerry, can you hear us now? Okay. Oh, there were some issues there. Can't hear you. Yeah, you're muted.
Yes, I can hear you.
All right. So Jerry is a distinguished professor in our department. He also holds an appointment in electrical and computer engineering. Dr. Stringfellow earned his bachelor's in materials science from the U and a PhD in materials science from Stanford. Dr. Stringfellow, please tell us more about yourself and your interests.
Okay. I am basically, what I'm interested in is how things work at the most fundamental level, and then using that knowledge to make products. And I'm going to talk about one thing today that is run through my entire career, and that is light emitting diodes, LEDs. I presume you know what those are and you've seen them. A light emitting diode is a piece of crystalline material like a diamond. It's a tiny piece. It's the size of a grain of sand. And when you hook it up to a battery, when it's in a certain configuration, you give energy to an electron. It goes up a hill and has higher energy. And then, due to a quantum mechanical effect, it can fall back down. And to conserve energy, it produces a photon. So this is what one looks like. It's not, oh, that's a green one. I was going to show you the red one because that's the first one. It doesn't look very red. But anyway, there are these tiny things that are taking over all lighting applications. Basically, the material science here is that the color of the light is determined by the elements that make up these single crystals. They're absolutely perfect single crystals. They really are like a diamond. They're gems, but we make them in thin layers called epitaxial layers. So I did my PhD work at Stanford on materials for blue LEDs. This was long, 30 years before the blue LED was developed. The blue LED was a very hard material to make. But at the time, just while I was a PhD student, people were able to make gallium arsenide, just gallium and arsenic in a diamond lattice, and it produced infrared light. And then people were able to add phosphorus to that, making an alloy, and then it produced the red LEDs. And I was going to try to show you one of these, but does that look red? It doesn't look very red, but anyway, that's the red LED. And that, my first job was at Hewlett-Packard Laboratories in Palo Alto. And Bill Hewlett had an idea of replacing slide rules, which most of you have never even seen. But that's how I did all of my work when I was an undergraduate and undergraduate student, with a handheld calculator. But the key was having a display that would work with battery voltages. And so when I got to HP, people were making red gallium arsenide phosphide LEDs, and that was my project, was to make those better. And after a couple of years, after the management had decided that I knew a little bit about what I was talking about, they said, okay, go away for 3 months and tell us where LEDs are going to go in the future. And so this is the thing that I'm most proud of. I developed a theory that told what the material would be, and that was aluminum, gallium, indium bonded to phosphorus, aluminum, gallium, indium phosphide. And that could only be grown according to a thermodynamic theory that I developed by a process called organometallic vapor phase epitaxy. It's a long name. And at that time, there were only 4 or 5 people in the world who were working on this technique, and it did not include HP. Well, HP wasn't sold on this, completely on this idea. I talked to management at all levels, and in the end, I ended up leaving HP because they didn't believe me, and came to the University of Utah. And HP missed out because I wrote a paper about all of this, and people in Japan, a couple of laboratories in Japan, adopted the material and the technique, made LEDs, and they not only made better red LEDs, they made green LEDs. This is a crappy screen, but that's a beautiful, bright, there you go, now you can see it, green LED, and you can make all the colors in between, orange, yellow, amber. So these devices are used in, for instance, traffic semaphores. When you look at a traffic semaphore, you see a red and an amber LED. They are made of these materials by this process. And so it's an outgrowth. I didn't do that myself. It took 1 million man-hours to learn how to make these things so efficient. But my first LED that I was working on at HP, you passed 1,000 electrons through this crystal and 1 photon came out. So an HP 35 was mostly a big battery. But now, when you pass 1,000 electrons through one of these materials, you get 800 electrons out. So they're 0.8% efficient. So that is something that, and I have to just add one other thing, and that is in years after this, people developed the blue LED that was where I started. A very tough problem, and it won them the Nobel Prize, Nakamura, Akasaki, and Amano. And that's in a material that's very much like the one that I was just describing. It's aluminum, gallium, and indium bonded to nitrogen, but it's grown by exactly the same technique, and the same thermodynamics control what's going on. And my work in recent years has been trying to understand the material sciences that make these materials so very efficient. So that's the LED story.
Thanks, Jerry. Next, I'd like to introduce Dr. Raj Rajamani. He's also a professor in our department. Dr. Rajamani earned his PhD in metallurgical engineering from the U. Dr. Rajamani, please tell us more about yourself and your interests.
Yes, I'm coming from the metallurgical engineering side. Now I'm in material science department. And, you know, my background is mineral processing. I'll tell you a little bit about mineral processing. We make metals like copper in Utah. And to do that, every day they have to crush and grind, 100,000 tons of rocks. 1 ton would be about 10 barrels of rocks. You can imagine it'll be 1,000 barrels being ground every day. So that's a process I studied, and I worked on the, just like chemical rate equations, I studied the, rates of breakage of particles, how to take big, huge particles all the way to 100 micron size. What is the rate of breakage and what's the energy required, and so on. I had studied chemical engineering in my bachelor's and master's degrees, so I had a lot of background in applied mathematics. So what I do is mathematical modeling of these processes. So in the early years, I worked on mathematical modeling of, grinding mills. And then I worked on mathematical modeling of hydrocyclones, a separation device for, removing, coarser particles from finer particles, or removing the finer particles from coarser particles, like that. And then later on, these grinding mills were consuming energy of the order of 15 megawatts. These mills run all 24 hours a day, month after month, year after year, and so on. So people wanted to study, how can we improve the energy efficiency? These mills are about, 30 feet in diameter. You can imagine 30 feet. Your room is 12. You multiply that by 3, 2.5, it's almost that size. Huge cylinder in which 600 tons of rocks and balls are moving around in a circle about at an RPM of 10 RPM, like that. So how to, how to study the energy consumption of this kind of thing, to reduce it from 15 megawatts to something like 14.5 or 14.2 megawatts. Well, the idea was to go back to applied mathematics. You can't get inside these mills and do any of these measurements and all of that. Only thing you can do is, use physics, just basic Newton's laws, physics of collisions. And except, you put up a huge drum and then hundreds and thousands of particles, sphere-like particles with various densities and so on, and then apply Newton's law to all those 100,000 particles and move the drum, and then use a big computer to do all these calculations. And we found out what are all the inefficiencies inside the grinding drum. And then we were able to change certain things internal in certain way so that we can reduce the energy by as much as 10%. And then coming back to recent years, I want to tell you something that I did. Your automobiles, there's, 80,000 or 100,000 automobiles sold every year. And you buy old cars, and then after about 4 or 5 years, you sell it for $20, it goes to the junkyard. And then, what happens? They take all these cars and shred them. And these cars have, mainly the body is, steel sheets. The rest of it, most of the bumpers, older cars, the engine, crankshaft and all of that, transmission, everything is aluminum, stainless steel, and so on. Majority is 70% aluminum. The rest of it is copper, brass and zinc and so on, like that. Unfortunately, after grinding, shredding all these automobiles, they were selling these millions of tons of this shredded, scrap metal to other countries because there was no way of getting this, aluminum out of the, aluminum out of the scrap metal. If you only get that aluminum, we can put it back, make engines again, and recycle. It's a matter of recycling. So about 15 years ago, I studied eddy current theory, and I'll just show you that. If you think of this as a magnet, round with a wire, and then I send alternating current, not direct current. And then I have a string, and right here, in the string, I have an aluminum particle hanging right there, about 2 millimeter, 3 millimeter, like that. It'll just swing up like that. If you put a copper particle, it'll just barely swing like that. So I studied that about 15 years ago, and there was a chance, the government came by and said, well, is there a methodology for processing 2 tons an hour or 4 tons an hour of this aluminum scrap and getting all the 70%, getting all the aluminum on one side and throwing away the copper and all of that. And using this principle, I struggled with it for 6 years with 4 or 5 of my colleagues and so on. It was blood, sweat, and tears on the 3rd and 4th year. I was almost failing, but somehow we got through. Today we made a machine, a belt conveyor about 2 feet wide and 6 feet long, on which this material, this scrap material will fall through. Underneath that, there'll be this same magnet that I just showed you, except it'll be a long rack and it'll produce a 10 kilohertz frequency. And as a result, the aluminum will jump, to a bin far away, and the copper and rest of the metals would barely just jump to a nearby bin. And we were able to separate that. That's an enormous success in this field, and I'm really proud of that.
Thanks, Josh. And finally, I'd like to introduce Dr. Zac Fong, who's professor in our department and currently serving as a program director for DOE's ARPA-E program. Dr. Fong earned his BS, MS in powder metallurgy from the University of Science and Technology of Beijing and earned his PhD in material science engineering from the University of Alabama at Birmingham. Dr. Fong, please tell us more about yourself and your interests.
Thank you. Okay, I have a career being, since the college days, I've been doing what's called a powder metallurgy, which is one branch of metallurgical materials or metallic materials development. And after PhD thesis, which I did powder metallurgy of tungsten, but I had 2 industrial jobs before I joined the University of Utah. That I worked in the industry for 11 years. And during those 11 years, I specialized on hard and super hard materials, and which are also, are what's used on for rock drilling. And if you think about oil and gas exploration, you think about today, we would like to drill less for oil and more for geothermal energy, right? We like to drill for carbon sequestration. However, rock drilling is important in energy exploration, in construction, in mining industry, everywhere. So with that specialty in hard materials and in the industry, I had 30-some patents, which gets some of them gets commercialized, and in the University of Utah, I continued that path of hard materials. So we invented what I called a functionally graded cemented tungsten carbide material, and and then we started a business, and we had government SBIR supports, and today that technology is being licensed to companies in US, in Europe, and in China, and it's being used as commercial products. And just 2 days ago, I want to tell you just one example of this technology working in the real world is 2 days ago, the Hilti, if you know Hilti, is the largest world power tool manufacturer for construction and demolition tools, right? If you are a home improvement guy, you know the Stanley tools, the Black Deckers, but the Hilti is the professional power tool company. They showed me a graph. They use our technology, and they make those drill holes in concrete. And when you actually Hilti, when this Utah Natural History Museum was built, and Hilti had a news item. When they built Natural History Museum of the University of Utah, they drilled I forgot how many million holes and using Hilti tools. But anyway, they showed that when they make those tools using our functionally graded tungsten carbide tools, and they life improved by 200%. That means that they are able to drill, 2 times more holes per drill, and that improves the efficiency and so on. So that's the super hard materials field, including the the synthetic diamond. Just one more point about the hard materials. You think about if you think about want to drill a hole in the earth of 5,000 feet, 30,000 feet down to the earth, and there's nothing, what do you know, can really survive that environment as to be cost effective, right? That's why the special hard materials are very special. Another invention we had is at the University of Utah in the last 10 years, we're involved in developing processes for making titanium more cost effectively. Titanium is a great material. It is a wonderful metal, and it has one of the highest specific strength. It can be as strong as steel, but only half of the weight. And for some applications like aerospace, you just cannot do without titanium. But the titanium is expensive. We don't see titanium in cars, in our personal cars. It should, but we're not. It's because it's expensive. So we've been focusing on, and we're funded by U.S. Department of Energy, develop processes to extract titanium metal and how to produce metal. And it just so happens, and now is the 3D printing, additive manufacturing is really gaining momentum, is getting really important, is the new revolution in manufacturing, and titanium is right in the center of it because it is, it's expensive material, so you don't want to use traditional machining methods where you waste 80% of the stock material you produce. It's expensive to start with, and then you throw away 80% of it, right? So additive manufacturing of titanium is very very popular, very developing very fast. So we came up with a process of making spherical titanium alloy powder, and that's to be feedstock for additive manufacturing. And we're able to, using our process, and cost of titanium powder can be only 30%, 20% what they make using plasma atomizing process today. And so that process is, within no time, we got a license to a large corporation in Pennsylvania. Now it's being commercialized. And we have several other titanium radiated technology. We're also doing it. And just for, we mentioned, innovation over here. So one of the ways we do this commercialization is University of Utah is especially good in this regard, is encouraging us to form startups, form commercial entities, and commercial entity, it becoming the the vehicle for commercializing technology that's developed within the university lab. So now the Dr. Simpson mentioned that now I have an opportunity to work at the Advanced Research Project Agency at the U.S. Department of Energy, and ARPA-E is for short. That's what's called. ARPA-E was formed 10 years ago, and it's sort of like a special force within the U.S. Department of Energy. Department of Energy has many different offices, for there's a fossil fuel energy, there's a nuclear energy office, and there's a energy efficiency, renewable energy office. But ARPA-E is there's a similar agency, Department of Defense, called a DARPA. But ARPA-E, best way to describe it is a special force agency that's in charge with coming up with new concepts and coming up with new programs that's not being covered by traditional roadmaps, and fund those, breakthrough ideas or new ideas, and that, and in order to, our mission is these technologies should lead to lower cost renewable energy, leads to a large scale reduction in the carbon emissions, in order to achieve the climate change goal in 2030 and 2050 to be and carbon neutral or carbon negative. So that's what I'm doing right now. I'm sort of on leave of absence from the University of Utah. And the program I just created and just announced the winner is what we call the Ultimate. The Ultimate is a program wanted to develop ultra high temperature materials used in gas turbines that's used on airplanes or gas power generation units. And these power generation gas turbines is the higher the temperature, the higher the efficiency. The higher the efficiency, less fuel you will use, less emission you will produce. So it has a huge impact on the economy of power generation. And there used to be these high temperature gas turbines are made out of nickel-based superalloys. And so in this program, and it is bragging here, it is my initiation. We're going using refractory metal alloys and to develop those new alloys that can withstand 1800 degrees C. Those, for the students over here, you probably never can imagine what 1800 degrees C is, and have those turbine blades to be made of. And congratulations to Dr. Taylor and Sparks and Dr. Ravi Chandran. They are one of the winners of this program. And so we hopefully a few years later, you were talking about the airplanes that are made out of refractory metals instead of nickels. And also, Mike, I wanted to let the students know over here, and the National Academy of the Inventors yesterday announced a new fellows of this year, and Dr. Zhang Ling is on the list. And so our department now has how many in this fellow of National Academy? 4 now? Yes, Dr. Jerry Stringfellow and Neil
Verkar, Dr. Stringfellow, yourself, and Ling Jing.
All right.
So we're very, very proud. Thank you.
All right.
Thanks, Zach.
Okay, sure.
All right. Well, now we're going to move into the questions section. Myself and Taylor will take turns asking questions of the panelists. For attendees, please remember to type your questions into the Q&A box so we can see those. If we don't see any of those, we're just going to ask you to speak up here at about 8:30. So we've got about 40 minutes that we can ask questions, and then we'll move to y'all's questions, which are really more important than my questions or Taylor's questions. So anyway, question number 1, and this is any of the panelists can speak up. I mean, we don't necessarily have to go through and everybody has to address this, but we kind of want to fertilize discussion here. Is what do you think is the next big thing for materials innovation to drive high impact technology development? So what can you propose, can some of you propose one problem that needs materials innovation? What's a technology that if we can just find that material, that magic bullet, a magic material that we'll be able to really make a big important technology development or leap?
So one that I would at least toss out right out of the gates, obviously coming from a space exploration background with SpaceX, is going to be better radiation shielding materials. Part of humans becoming an interplanetary species requires us actually going into space and surviving on our trip to other bodies within our solar system. So one of the key problems that we have with that is the amount of radiation that people are going to be exposed to during those trips, which can span, days, weeks, months, depending on where you're going within the solar system. So there's, different types of systems that make a lot of sense for radiation shielding materials, such as even polyethylene. However, there's got to be some serious room for innovation to create very lightweight materials that block a lot of radiation that enable humans to safely travel to other bodies within the solar system.
So can you specify which forms of radiation, like gamma radiation, ultraviolet rays, neutrons? What's really most important for space exploration?
So pretty much anything that's going to fry your cells. So definitely blocking a lot of the gamma radiation, anything coming from the sun that's going to be penetrating the spacecraft that you are traveling in throughout the solar system, making sure that, as few of those energetic particles reach our bodies as possible. There's certain things that make a lot of sense. Hydrogen atoms work very well for a lot of this type of shielding. However, a lot of the materials that contain a lot of hydrogen atoms aren't necessarily the things you want to take to space in those types of quantities and then also radiate. So water is a decent shielding material for humans in space. However, it's very heavy, and if you're irradiating it, you can no longer necessarily use it for consumption for substance of life.
Can I suggest another one?
Yeah, please.
This is a giant one, of course, and it's climate change. And material science is right in the middle of climate change. I talked about light emitting diodes. That's one approach, is producing light, and LEDs are at least 10 times more efficient than incandescent lamps. So that's one aspect. Another aspect is generation. We have very efficient solar cells these days, but they're very expensive. We need to have materials and processes for making better solar cells, and not just solar cells, but other ways of generating energy that don't produce carbon. And of course, batteries is part of that too. So it's a gigantic field, but materials is right in the middle of almost everything related to climate change.
I'll second Jerry on that. That's the mission of ARPA-E. You know, you guys have good ideas, and let me know. I'll create a program on it.
So maybe maybe building on that, you obviously want to prevent the carbon from getting out there to begin with, but once it's out there, I think we also need technologies to capture, say, CO2, and having the materials to remove CO2 once it's been emitted will be, I think, another important category of material science.
Yeah, ARPA-E has programs on direct air capture and direct ocean capture. The CO2, because a lot of CO2 gets absorbed in ocean water. But you know, along this line about climate change, so I think under the umbrella of energy and the environment and climate change, and there are many materials issues. Just to name a couple, one is hydrogen storage materials. You know, if we could drive fuel cell cars, and we would be even better than the electric battery today. Cars today, you know, electric battery cars is now becoming on the way becoming the mainstream now. And however, fuel cell vehicles would be even better because you know, it burns hydrogen produces the water. But current challenge is we don't have a good way of store hydrogen, carry it on board. And so this hydrogen storage material is a very important one that would lead to a breakthrough. And if we can do that, then transportation industry will not become a polluting industry. It would be becoming a clean industry. I can give you other examples, but I'll let the others speak.
I had one I wanted to bring up really quickly. So I'm just kind of building up on this environmental impact that we've been discussing right now. I mean, like, you know, it's Christmas time of the holiday season, and we keep getting Amazon packages to our house, and everything is wrapped up in plastics, these boxes. I mean, so boxes at least are recyclable. Some of the plastics are recyclable, but some of them are not. But I mean, there's just these things that are used to protect the things that we buy, and some of the things that we've been using are just single-use products as it is anyway. And so all of it kind of makes me feel guilty when I see this sleeve of plastic that I get something in, and I know that if I throw it away, it's going to sit in a landfill for hundreds of years. And so I think one of the big things that material science needs to focus on is just how do we make materials that are, like for packaging, for example, that are just, they're not going to last for a long time. They serve their purpose, and then they're just gone. They don't just sit in the environment and take up space.
Yeah, that makes me think of when I purchased my treadmill recently. It came with so much cardboard and like a wooden pallet. I think it took me 3 weeks to get rid of all the waste, to have it all picked up. I felt really bad about that. So I'm totally what I should mean about the packaging problem. Other ideas, other suggestions on big material innovations we need?
I would even add just longevity of materials to the list. and kind of creating the mindset of things lasting further too. So, you know, it wasn't too long ago that you'd buy a refrigerator and it'd last 30, 40 years, right? And now things have been designed to last a lot shorter of a period of time before failing, that if we changed our mindset into using better materials to have things last longer, that it would definitely go a long way to reducing that waste as well.
Yeah, I think your company's doing a great job demonstrating that with the reusable rockets and the boosters. It's really amazing stuff. Seeing those rockets land after they've done their job. Other ideas? We move on to the next question. Okay, Taylor, you want to take it? Or Raj, did you have some?
Hello, can you hear me?
Yeah.
Okay. I just want to tell you, just like on the recycling side, every year we are throwing desktop computers, definitely throwing a lot of desktop computers, and then we are throwing away laptop computers and then cell phones and so on. And all of them, these are called electronic waste or e-waste, and all of them have very valuable, you know, little tiny metal in it, that too coated with silver, gold, and platinum, and so on. So all of them can be recovered easily by shredding them and then catching the metals only and bringing it back and so on. And for that, what we need is a material. You know, I talked about alternating field magnets. When we use the alternating field magnet, you know, we need a high field, 2 Tesla, 1 Tesla, and so on. You can do that with steel. The moment you wind wire on steel and then subject it to 10 kilohertz per kilohertz current, all of a sudden the steel gets hot within about a minute to about 200 degrees centigrade, and it's unbearable. So we were looking for thin materials, thin sheets of steel stacked with the insulator like that, tried so many of them. If only we could find a material that'll exhibit, you know, 1 Tesla magnetic field at 10 kilohertz, it'll be a great advancement in recycling electronic scrap. Thank you.
Yeah,
that is a very important area, yeah.
Well, our next question is related to how your degree studying material science has prepared you for your career. So were there specific subjects that you studied that you found to be really important either in your career or specifically to being an inventor? What comes to mind?
I'll go first. I think what our education, I my old professors in the back, you know, what we learn about in physical metallurgy, basically the physics of metals, right? They you know, they study the correlation between structure of materials, its correlation to the properties. And that's one thing I found is important throughout my career, is whatever you wanted, I think, you know, remembering that principle, remembering always go back to the structure property correlations is what's very important for, you know, identify a problem and trying to solve the problem and trying to improve the material. You have to change the structure. Or thinking is if someone tell you something material is behaving differently, is better or worse, and so on, is always a reason in the structure. If you cannot identify that structure change or microstructure change, you don't understand the problem.
Could I add something? I think it's both people and things that matter to me. Seeing Willa Cutler there reminds me that my mentor when I was an undergraduate was Ivan Cutler. When I met Ivan Cutler, I was going to study either physics or electrical engineering. This guy had so much charisma, you know. He talked me into believing that if we could solve materials problems, we'd change the world. And so Ivan Cutler is right up there with superheroes. And that's the thing about it. Professors can have that kind of an impact. But in terms of stuff you learned in the classroom, thermodynamics was the thing that changed my life. I could really understand how things were happening after I had this thermodynamics class from George Hill. He was in metallurgy at that, or maybe it was fuels engineering at that time. Suddenly I could understand why when you heat water up, it goes from ice to liquid to vapor. And I can still remember the thrill that I felt. And it's gone through my whole career. Thermodynamics has trying to understand things that happen in semiconductors.
So a couple that I would add to this that have made me particularly successful in my line of work, in addition to what Professor Fong brought up with physical metallurgy and understanding the mechanisms that drive better materials in general, would also be the side of processing. So metals processing is a class that I took that helped me immensely to understand the different ways that you can get from point A to point B with different materials that then influence the physical metallurgy of those materials. And when you factor those together with something as powerful as statistics, you now have the ability to really cater and design specific materials to end up achieving exactly what you want. One other course that assisted on the back end of that is going to be evaluation of materials. So taking a look at a fracture surface and understanding why it failed, whether it was fatigue or whether it was, any other type of failure that you can experience in materials, to then understand why, because then you can close the full loop and go back with understanding why something failed to looking at the structure and the processing, and then using something as powerful as statistics to bring all of that together to end up being able to design new materials. And with this type of group of skill sets, at Spacex, I've been able to invent a new high temperature solid solution strengthened niobium alloy, as well as a oxygen dispersion strengthened niobium alloy, both for high temperature rocket applications, by combining these different topics.
I'd say in my case, the most used academic courses were probably in materials processing and fracture mechanics. But I think maybe in addition to the academic subjects, I think the problem solving skills, the ability to work with others, and the ability to represent your ideas. You can have the best idea, but if you can't either sell it internally or externally and convince others that it's a great idea, it will die on the vine. So I think some of those other skills that you learn either as an undergraduate or a graduate student can serve you well throughout your life.
I wrote down a bunch of classes, but I would say that the one that probably sticks out the most to me is organic chemistry. So I took OChem 1 and OChem 2. And I remember asking a lot of questions because it was taught by the chemistry department. I kept wanting to know, like, are these solids, are they liquids, are they gases? Like, what is the physical structure of these? What kinds of properties? Are they slimy? Are they hard? Like, what are these things going to be that we're making? And I remember that I raised my hand and asked that question in class. And the professor said, you know what, just focus on the chemistry right now. We don't need to worry about that other stuff. But I love that those questions were answered in material science and engineering. So, I mean, organic chemistry is super important for polymers. So that's probably the most fundamental course that I have to base all of my work on. But there are two others. One of them is called Bioinnovation. More than anything, it was just a year-long class, an 8-credit-hour class. That was just all about innovation, all about how to think outside the box, how to solve problems. We followed the engineering design process, and I thought that was really impactful. And then the third one I wanted to talk about was kind of like a, just a really specific niche class, but it was called drug delivery, but it was the hardest class I ever took. And so the reason why I think that class was important is because they expected that we knew every single thing, every chemical reaction, just everything that was happening. And so it really forced me to work really, really hard. And I felt like I learned so much just because I was forced to work so hard and to learn something.
Raj, anything to add?
I studied a lot of applied math. And so anytime I look at all these processes, including chemistry, I always say, why do we have to do experiments? We can turn all of this into applied mathematics and really run it on large computers and look at all the modeling, that's called modeling, look at all the results and so on. And isn't that, Taylor, you talked about artificial intelligence applied to materials. There was a seminar that you conducted. Can you tell me, that field, I wish I had learned that long time ago. I would have worked on it.
Yeah, I mean, I think it's very much on the forefront of material science. It's taking a lot of the packages that we had in the past, but nowadays we have compute power and advanced algorithms that allow us to do statistics in fascinating new ways. Machine learning, it gets hyped up that it's gonna be able to do everything. And I think that we're now running into a lot of the challenges that it faces for materials research. But at the same time, that's opportunity to develop specific tools and tool sets that address machine learning for materials challenges. So topic for another day, but I think that that's pretty exciting stuff.
All right, so the next question, I think this question is probably mostly for Willard and Gavin, but please, anybody who has experience with this can speak up, is how much leeway does your company give you to explore wild hair invention ideas that might not go anywhere? And I say Willard and Gavin because the rest of y'all work for universities, and that's pretty much all we ever do is work on wild hair ideas. So, but working for a company, we imagine the culture might be somewhat more challenging to do that sort of thing. So can you guys speak on that?
Sure, I can go first. Obviously, working for a company, they generally are interested in generating revenue and profit. So there are certain goals that you need to achieve in terms of developing new products and timelines. But with that said, certainly there is a portion of the money that and people and talent that I'm responsible for, that you have some leverage and you can explore new ideas. And I think many of the great ideas in history were actually discovered on the path to somewhere else. And people who are observant say, start connecting the dots. And so, we do encourage people to do a little exploration on the side. And when people come into my office and say, hey, I had an idea, we talk through it. But I think generally, if it's not costing hundreds of thousands of dollars, try it out and, try to fail fast. So I think there's some ability to work on the side, and certainly if it's a great idea, it will, I think following it will lead someplace that, again, if you're good at selling your idea, can become an official idea as opposed to a little side project.
So from my experience, working at SpaceX has been an extraordinary experience in this type of way, where SpaceX traditionally assigns their engineers big problems, right? So we have this problem, nobody knows how to do it currently, put together your best ideas, and that usually would include a couple surefire ways that are probably usually either longer to manufacture or more expensive, as well as maybe a couple of these, crazy out there pie in the sky type ideas, which theoretically should be very cheap and very fast, but require a bit more development and are a lot higher risk. So we've usually had the ability to go out and create these custom types of solutions and work them in parallel to the more conservative, like surefire type of solutions that you can also work. And this is where, I brought up two different niobium solutions that I invented for, one of my last major projects, one of which was a little bit more of a safer solid solution type strengthening new alloy that I invented, which is a more conservative way to iterate on niobium alloy technology, as well as this kind of pie in the sky oxygen dispersion strengthens niobium alloy, which is where you actually end up forming little tiny oxygen ceramic beads inside of your metal matrix in a very simplified type of manner, which ends up giving it a lot of strength. Ceramics behave very well at high temperatures. So given the leverage to experiment with some of this powder metallurgy and creating this oxygen dispersion type niobium alloy, we ended up creating several solutions to the same problem, where we got to explore some of these kind of more pie in the sky type ideas, as well as kind of the more conservative approach. And then at the end of the day, you boil that all down and pick the best solution for the problem at hand. And you know, I've seen this happen time and time and time again across SpaceX culture and company, where sometimes the conservative one ends up winning out because it just makes sense. And sometimes you end up with this really clever solution on why something works. And one really good example of that pie in the sky type idea is when you watch the Starlink satellites deploy from a launch. What's actually happening is that your second stage is tumbling end over end. There's a pin that pulls down through the center of that stack of 60 Starlink satellites. And since it's tumbling end over end, the satellites at the top of that stack deploy faster than the ones at the bottom of the stack. So that's how they actually separate away from each other, is because they have a different inherent velocity tied to just the way that it was set up. That was insanely risky the first time that was ever attempted, though it made perfect sense on physics and by looking at the numbers. And it ended up working out great, and it's what we do to this day.
Thanks, Gavin and Willard. Anyone else want to make a comment based on your experiences? I mean, I know not all of you have worked in university all your life. I know that Jerry and Zach had other lives before.
Well, let me just say that, I mean, I mentioned it when I was introducing myself, but at Hewlett-Packard, this was Hewlett-Packard Lab, though, so it's you have more room to explore, but you always had officially 10% of your time to do things that you thought were important, and they would support you. That was an electrical engineering place at that time, so they were building instrumentation and things like that. And so what they were talking about, resistors, capacitors, and transistors in those days. But the problem was, what I wanted to do cost hundreds of thousands of dollars, and that's where we ran into to a little difficulty, and that's why I ended up leaving. Of course, then I had to find the hundreds of thousands of dollars myself, and so that's a bit of a problem. But I've always loved, I have to say that I've always loved the freedom of academic life.
Well,
Right.
our next question is, you know, on your path to inventing things, what do you find to be of greater importance? Is it being able to select from existing materials, or is it the discovery of new materials? Can you comment on that in the inventions you've been involved with?
To jump into the silence, I guess I'll just take the first crack at this. So there's a famous Elon saying that we get told all the time, and I'm going to say material in place of any other word that could go here. And essentially, the best new material is no new material, right? And that goes with a lot of different things. That being said, and he's very quick to follow up with this, the materials that we've been using for a very long time are typically materials that are designed with versatility in mind. So you look at a lot of the steels that are out there, they're good at corrosion resistance, and they're good at strength, and they're good at these things that are good for a very wide variety of applications. And the way that products are developing and maturing, we require very specific materials for very specific applications to eke out every little bit of extra performance, whether it be, you know, in terms of ISP, rocket performance, or, you know, even terrestrial type applications or anything else. That the more specialized that we get with all of the products that we're making, the more specialized materials we need, and these wide variety type, you know, materials that fill a lot of needs are no longer quite as suitable, and they need to either be improved upon or replaced completely with very specific materials for that exact application to be as efficient as possible.
Yeah, I think
in semiconductor materials, there's no doubt about this. If you want a new color for a laser, let's say, or a light emitting diode, you have to invent new materials, and it's going wild these days. The alloys that people are producing, they're not even stable structures, but you can use kinetic stabilization to make these new materials that have amazing new properties. And so that's a fun thing about semiconductors, is that we're inventing new materials all the time rather than trying to use old materials.
I think as Gavin said, that your first course of action is always, can I use an existing material? But we have spent a lot of time and money developing not only new materials, but a new way, a new process for making that material cost effectively. And so you always have to balance a new material versus a new process for making an old material. And unfortunately, there's some problems that just require new materials. And that allows many of us to stay employed, but it's also quite interesting. And it's, I think, very satisfying to work on a new material, to see it go into the marketplace, and to be able to look and say, hey, I contributed to that. And there's still so much to be invented. I think one of the things that I learned as I did my PhD is more and more about less and less. You narrow in scope, and you realize that there's just about every topic you can go deeper. And there's always more to learn. So I think for those of you in the audience, there's a bright future in material science, and there's a lot of things yet to be discovered.
So I had some thoughts about this. I like the question, and I actually think they're both really important. So I think the most important thing is to be open-minded before you try to solve a problem. So like in some cases, the material already exists, and so you're just finding the right one for the problem that you're trying to solve, but sometimes that material just needs a few tweaks. But I think it's really important to build upon the work of others and not just reinvent the wheel all the time. But I love developing new materials. So sometimes when you're looking, so like what you're looking for just isn't out there. So in either scenario, it's up to us to put together a good list of requirements for the problem that we're trying to solve. So once that list is put together, you'll have your pass-fail criteria and the characterization methods that you're going to use. And then whether you find the right material or develop the right material, you'll have something that actually meets the needs of the user. So sometimes we do those in parallel with each other. It's like, okay, here are the materials that exist that kind of meet the parameters that we're looking for. And here are the ones that we're making, the different compositions that we're making. And we just test them all together to see which ones meet the needs the best. So I just think meeting the needs of the user and being open-minded by understanding the problem completely before you try to solve it is really important. And then otherwise, you're just trying to wedge a preconceived idea sometimes as a solution into a problem that may not fit all the way.
Any other thoughts about this question? Okay, the last question from between Taylor and me. Please share a story about a personal hurdle or obstacle you faced in your work and how you overcame it. No obstacles. Everyone's has been a fantastic success.
I can tell you an interesting story. As a young scientist, we had a large automotive company that came to us and said, hey, we've got a part on this car that's melting. It's exceeding 1400 degrees C. That's pretty hot. You don't want a heat seeder that's like that. And so they also came with a suggestion to say, hey, we need you to develop a higher melting temperature material to solve our problem. And that sounded pretty logical to me as a young scientist. So I spent months and months, gave them a material that could melt at 1650 degrees C, about 3000 degrees Fahrenheit. And you'd think that would solve anybody's problem. Unfortunately, they also melted that material. And what they thought was the solution actually wasn't really the solution. And as we dug into the application, as I learned more about it, we discovered that actually, you know, it was heat capacity of the material was also quite important, because as you're bringing heat in and creating an exotherm, you can either, you know, take that heat away in the flow, or you can absorb it. And it turned out that we needed both a high melting temperature and a high heat capacity. So then we had to develop another material that had also a high melting temperature, but also a high heat capacity. And it survived their application, and you know, now we've sold more than $1 billion worth of that material for this application. So it was a great example for me of, you got to solve the actual problem, not just find the solution that somebody prescribed for you.
My comment would build upon one of Willard's previous points of essentially that the soft skills, right? So you can end up coming up with a great solution to problems, and the powers that be sometimes resist change. People tend to really like the status quo, especially, you know, a lot of people down on the floor, technicians, people assembling stuff, tend to not really like a lot of change. So being able to sell your ideas and to be able to get the buy-in from everybody that's involved in this, whether it be the high-level stakeholders or the people that you're going to be down on the floor with trying to make this work for the first, second, third, fourth time, is very, very important, that the set of soft skills. So that should never be underestimated. And what I would close out that statement with is something that a very wise mentor of mine once taught me, and that's never underestimate the political power of donuts.
And other stories to share, including eating donuts, favorite donuts? Simon Cannon says donuts are a powerful motivator. Thanks, Simon. Okay, well, there's no more stories to share now. We can jump right to some of the questions that our audience has been asking. There's some really good ones here. And know that Zach has been typing some answers, but I'm gonna pose some of these questions to the overall panel. And I think one of the best questions I thought was, how did you know you wanted to go into materials and metallurgical science engineering? Why'd you pick the major? Anyone?
I didn't know until later. Oh,
Well,
sorry, go ahead.
I already expressed some of this. I was trying to decide. I loved, of course, science and mathematics, and but in the days when I was a freshman, each of the department chairs got to make a presentation to the incoming engineering students. And again, it was Ivan Cutler. Ivan Cutler made me believe, this is Willard's father, by the way, made me believe that there are infinite possibilities in material science. You know, there's so many things that you could do that made a difference. And so this one charismatic seminar that I went to changed my major to material science.
Oh. Jeff?
Okay, so I actually did my bachelor's degree in biology, and I minored in chemistry. And so what happened is I was working on a senior project with these microscopic transparent worms, and the professor I was working with said, okay, here's what we're gonna do. And I was like, oh, that sounds good. And so I said, but then can we do this, this, and this? And he says, Jeff, we're not engineers. They're on the north end of campus. And I was like, I thought that up until that point, engineers only worked on circuits, wires, and bridges. And so I thought, I hadn't even considered engineering at that point. And so, but all the questions that I had, I already told you I was asking questions in chemistry. Like that was in general chemistry as well. I always wanted to know, like, what is the structure of this thing that we're looking at? What are the physical properties of it? And so later on in my life, I discovered that all of my answers would be found in materials science and engineering. And I just thought that that was the most exciting thing I could ever possibly do.
Yeah, Now, maybe since Jerry's let you know that my father was a material scientist, you might think that I would naturally have a proclivity for material science. I was probably the only kid who grew up with a high temperature kiln in their garage. But, and I just used it in the winter to open the door to heat the garage. But I actually came across material science a little bit accidentally. Unfortunately, my father had passed away by the time I was in college, and I really had no interest in material science, although I was quite familiar with it. And through a series of quirks, I was waiting to get admitted to another major. And I went and talked to the material science guys and said, hey, can you let me join your department for a while I'm waiting for this other major. And I ended up getting admitted in material science, and I stayed. And then I thought, I will, just work as a material scientist for a couple of years. I got a job with Corning, and I said, I'm going to go get an MBA or become a patent attorney or do something like that. But when I started doing material science as a job, I found it fascinating. And as a result, Corning sent me back to school and paid for my PhD. So it was kind of an accident for me, but it's been a very fortunate accident and one that I have not regretted.
Cool. Anyone else want to share their story of discovering materials or metallurgical engineering? Taylor, come on, you can join the panel.
So I have only had limited experience in inventing things, but I'll say that we were working on these electrochromic ski goggles a while back, right? The idea is that you could hook a little battery up to your ski goggle lens, flip a switch, and it could change its transparency in real time. So these are coming into the market now. There's a couple companies doing it, and we were racing as fast as we could to get it to the market. And I just got to say, it was so fun to take it out of the hypothetical and actually make something, and not just make something, but make something we were going to show to somebody to try and sell it. That was a really fun experience to me. I mean, we begged and pleaded and used every sort of connection that we could get in the office room with the VP at Scott Goggles. And foolishly, we were too cheap to buy nice goggles because we were just destroying them as we made these things. So we'd go to DI, the thrift store nearby, and buy goggles to use as our templates. And we bought a pair of Smith goggles, and I thought it was so great to walk in there. And the first thing they said is like, what are you bringing this pair of Smiths in here for? That's one of their big competitors. So anyways, I think that there's a lot of fun to be had in actually translating things to as an inventor, because you think you understand it, and then you realize it's far, far more complicated. And, a class that Jeff and I teach together is Materials Innovation, which is all about commercializing products. And one of the textbooks we use reiterates this concept of build, measure, learn. And I love that methodology, that mentality of build something even if it's not perfect, build it so it's good enough that you can measure something with it and learn from it and iterate it and make it better and better. So that's something that that's a hurdle that I like to overcome, is, trying something out and decoupling your pride from recognizing this. I know this isn't my best product, but it's not supposed to be. It's supposed to be good enough to measure something, and that's been a fun process to go through.
Great. Favorite material to design or work with? Zach says titanium. Titanium is fun. I like molten salts. What do you guys like?
Hydrogels.
Hydrogels. What makes hydrogels special?
Well, the thing I like about them is they're stimuli responsive. So if you put them around something, then they'll change their properties. So like they'll swell. So you can use them for sensors, you can use them for drug delivery devices, you can use them like in soft robotics as an actuator. So I just think they're really versatile, and I like them.
Nice.
So my comment would be high temperature refractories. So nature tends to have this ironic balance within it, where you know, very, very high temperature materials, ceramics are fantastic for a lot of these applications. However, they're very brittle. So by the time you need any ductility in a very high temperature application, you're going to need to go to a metal. And all of these high temperature refractory metals have this massive Achilles heel, which is where they form these oxides. So essentially they start to break down in the presence of oxygen or air, atmosphere, at these higher temperatures. So they behave very well at high temperature, but they also break down at high temperature. So they typically require a coating or some other type of surface modification to protect them. So it's this fascinating balance where the things that perform best for the application also are inherently terrible for the application without materials science really making them stand out as being an awesome material for that application.
Well, this is not a surprise that I'm going to say semiconductors. And it's because our whole world is based on semiconductors these days. Silicon is the semiconductor that allows us to make integrated circuits, computers that'll allow us to do AI solutions to materials problems. But the really, really, really interesting thing that's happening in semiconductors today is making tiny, tiny nanometer size semiconductor wires, dots, and the surprising thing is, the wonderful thing, I mean, we all learned this in quantum mechanics. If you take a red material, I was talking about red LEDs, and if you make the particles smaller and smaller and smaller, the light that comes out turns from red to green to blue. It's wonderful, the phenomena in semiconductors, and the wide scope of semiconductors makes them very interesting materials.
Nice.
I think for me, it's got to be high temperature porous ceramics. And normally in the world of ceramics, people try to avoid porosity because porosity leads to flaws which are strength limiting. And much of my life is spent at the other end of the spectrum. I'm trying to add as much porosity as possible to either create paths for gas flow, for filtration applications, or to limit the mass. And balancing the ability to have adequate strength with nearly no actual material is some tricky material science and processing.
Okay. Another question from the audience is, what key features or characteristics lead material scientists to be successful entrepreneurs?
I think you got to be optimistic, and you've got to be willing to take some risk. And as Taylor indicated, be willing to iterate, because you know, the beautiful thing for me, at least, about material science as opposed to somebody who's in theoretical physics is we can create hypotheses and to test those hypotheses and then iterate. And you know, most of my ideas are wrong, but I can test them and retest them, and whether it's a physical test or a model, and eventually find the right solution. And I think that's really the fun part about creating something, is finding all the things that don't work and eventually finding a solution. So you got to be pretty resilient and pretty optimistic to want to work in this space.
I like what Willard said. I would just like, so I love the risk taking, but I also think you need to believe in what you're doing. If you don't believe in it, then I think you're not going to go very far with it. And I do love the iterative processes that are involved with it. So, and part of that, I guess, comes along with just being able to take really harsh criticisms from people, like users, from people that might invest in what you're doing. It's, you know, people are pretty pretty harsh sometimes. But if you can take it and you can make changes and kind of take a step back, I think that's a really important attribute.
Okay, great. Let's see, another good question here, I think, from Grayson Kohler. I'm a physics major who wants to go to graduate school for MSc. Notice a lot of people mention that their understanding of the fundamental physics helped them in solving problems and innovating, which is great to hear. That being said, what were the specific technical skills you had that helped you innovate and solve problems? Are there technical skills you've used for many of your innovations like SEM, modeling, etc.? Of course, it depends on the problem, but I'm curious if there are ones that translate to many fields within MSc.
It's hard to pinpoint. I was reading that question. There's no simple way answer. I think this person asking question already mentioned, the materials characterization skills are very important. And in order to understand the structure, you have to characterize the materials. But in the modern days, of course, the modeling and machine learning becomes very popular and looks very powerful. So in the end, it's going to be a combination of those skills, and also it takes collaboration between team members with different skill sets and to work together to solve problems.
Well, I was wondering, I was reading this about Jerry, about how much quantum mechanics do you have to know to be able to develop LEDs?
Well, I was going to chime in here. I've had 40 PhD students over the years, and some of the very most successful students I've ever had have come from the physics department. They have the basic understanding of quantum mechanics is one of the things, but physics in general, and they make darn good material science graduate students, and these are people who go far in their fields. I'll tell you, one of my students is the chairman of the biggest light emitting diode company in the world, and he started out in physics. So physics is a great basis for material science.
Right.
I would say one of the skills in material science, everybody talks about different processes. There is temperature, pressure, and this oxide and that oxide mixed together and all of that. And if you want to get it to the highest property and so on, process engineering statistics is a good principle to learn. There you study what is called design of experiments. And once you have that, you can do a few experiments, as little as 4. And then from that, you would be able to tell which direction I have to move in order to maximize this particular property. And then do some more experiments there. And one more time, you will get to the peak of the highest property that you are seeking for. The question says something about modeling, so I offered that answer.
Okay, thank you. Maybe this will be the last question of the night. What impact do you see nanotechnology having on improving battery technology?
Well, nanotechnology is a general term referring to many things, but if it can be many things, but one of the meaning is using very small scale powder and particles, and so in that sense, nanoparticles, nanotechnology already making a tremendous impact on battery technology. Yesterday, the MRS awarded the top honor to Professor Trey Yi out of Stanford for applying nanotechnology to lithium-ion battery. He is the inventor of using silicon for anode materials.
Okay. Other thoughts?
Well, if you think of nanotechnology as things at the very fine scale, it's in nearly all of material science. I mean, on the battery comment, there was a big announcement yesterday or the day before by QuantumScape on a solid state battery using a ceramic electrolyte. And while they didn't give all the details, I'm sure that they're at the nanoscale, there's a lot of electrochemistry happening that is critical to the battery's success.
Yeah. So I noticed a question here that that Raj was going to answer. The fact that a lot of the innovations require very expensive equipment for characterization, processing, etc., makes me think that larger institutions will own the vast majority of the intellectual property as it relates to materials. Do you think this will be an issue, or have any other opinion on this? Raj, did you want to answer that one?
Yeah, I'll just start off like that. I think, Taylor Sparks can speak to that. We have all of the characterization equipment in our department, if not in the larger campus and so on. And we don't have to be worried about intellectual property owned by larger institutions. Whatever we work here, we can apply for IP or intellectual property. We have a, technology development office. And even before doing all the experiments, you can just do a principle, IP, write that down and it is protected. And then after that, you work on that. And the IP comes to fruition, and later on, based on that, you can apply for patent. I know Zac Fong has applied for patent, and Jeff Bates has done lots of IPs, and Dr. Stringfellow has done many, and so on. That's not a problem at all in our department.
I think there's kind of been a movement, not just at the university scale, but at city scale, where you're seeing more and more maker spaces becoming available that have pretty sophisticated tools. I don't know if I've seen a lot of characterization tools there, but laser manufacturing and quite a bit of other things are now becoming quite popular in most major cities. But then Raj is right that there are centers on universities that allow internal and external. So you could be a garage inventor and come up and use our microscopes or whatever else, certainly at the University of Utah. And I hope that that's a model that's happening more broadly across the United States, other universities as well, to lower that barrier to entry so you don't have to be a millionaire to have an idea. You can be a garage inventor and just use a resource when you need to.
Any other thoughts on that? Anyone want to share any closing thoughts or words of wisdom for the students that are have signed in or that will be streaming this later?
So I'll kick it off. The key way that I would close anything that I have to say about the University of Utah, the Department of Materials Science and Engineering, Metallurgy, all of it together is, from my own experience, I can say that I have one of the most well-rounded backgrounds out of a lot of my peers, where a lot of my peers have been almost entirely focused on, computer modeling or other very specific aspects of it, where throughout my education, I was exposed to everything from being on incredibly hands-on through lab experiments, understanding, how to go from dirt to metal to part, and essentially just how to think and solve problems in general, that it kind of really delivered that whole package of how to be a really good engineer and how to solve problems using fundamentals and evaluation techniques, rather than, a super laser focused single aspect of something else, that it really delivered me to the workforce as a well-rounded engineer.
I can endorse that as you'll get a great education at the University of Utah, and you can compete with anybody anywhere. I was a little bit nervous kind of going out into the world saying, I'm a poor old, University of Utah graduate, but you can compete with anybody from any background. And I think it should give you a lot of confidence that you can succeed. So hopefully you guys will make a decision to join material science and engineering and make the world a better place.
Nice.
I had two thoughts about this. So first of all, I always tell my, so I get to teach the freshman class. And so I feel like my job is to inspire them. And the thing that I like to tell them is that Material science and engineering and metallurgy, they're just so important that every single technology that comes out of all the other departments is only as good as what we're able to come up with in our department. So first that, like I think it's just a big impact. But then second, just putting in a plug for our department, I mean, there aren't that many students. So the University of Utah is pretty huge, like 35,000 students, but our department graduates like, 30 to 40 students every year at most. And so they have a really strong sense of community. They're always studying together. They form lifelong friendships. I'm friends with a lot of them on Facebook, and they're all friends with each other. And some of them asked me to do a book club with them. And so I just like that we have this small community at this really big school.
Are there other closing thoughts? Well, thank you so much, guys, for doing this. Thank you for the attendees for listening, and really pleased how this turned out. And hopefully we'll do it again. We'll do it again soon. So,
Good night.
good night.
Okay.
Good night, everybody.
Bye.
At all.
Right.